In the morning, we were discussing about the Navier-Stokes equation, and in this session, we will be talking about some very simple exact solutions of the Navier-Stokes equation. We have already discussed that the Navier-Stokes equation it represents a system of equations which is a nonlinear and partial differential equation. So in general case, analytical solution of that is difficult. However, there are some special cases in which we can work out the analytical solutions of the Navier-Stokes equation. So before coming into that, let us write the Navier-Stokes equation again for incompressible flow. This is where we stopped in the morning, and we will take it up from here. So let us take an example with I equal to 1. I equal to 1 is nothing but the x momentum equation. So rho del u1 del t plus, here there is a repeated index, you see, uj and xj. So j is a repeated index. So we can write rho del u1 del t plus u1 del u1 del x1 plus u2 del u2 del x2 plus u3 del u3, this is del u1, u3 del u1 del x3 all these are u1 in the numerator, minus del p del x1 plus, here also you have a repeated index, that means there is an invisible summation. So del x1 of mu del u1 del x1 plus del x2 of mu del u1 del x2 plus del x3 of mu del u1 del x3. These three terms plus b1 for I equal to 1. So instead of the index notation, many times for solving problems analytically we use xyz notation. So instead of x1 we can write x, x2 we can write y, x3 we can write z, u1 we can write u, u2 we can write v, and u3 we can write w. These are absolutely equivalent notations. So if we do that, it is possible to write this as rho del u del t plus u del u del x plus v del u del y plus w del u del z is equal to minus del p del x plus del x of mu del u del x plus del y of mu del u del y plus del del z of mu del u del z plus b1 bx. This is nothing but the x momentum equation. Similarly, for I equal to 2 we will get y momentum, and for I equal to 3 we will get the z momentum equation. So let us write the y momentum and the z momentum equations. So I equal to 2 y momentum. Similar thing as the previous equation, only difference is instead of u it will be v. So rho del v del t plus u del v del x plus v del v del y plus w del v del z is equal to minus del p del y plus del del x of mu del v del x plus del del y of mu del v del y plus del del z of mu del v del z plus by. And finally, I equal to 3 z momentum. Similar thing as the previous with v replaced by w. So rho del w del t plus u del w del x plus v del w del y plus w del w del z is equal to minus del p del z plus del del x of mu del w del x plus del del y of mu del w del y plus del del z of mu del w del z plus bz. Now you can see that these equations are lengthy if you write it in expanded form. Many times that is why we write in the index notation, because it is much more convenient to write these equations in index notation to make it compact. But whenever you are solving it analytically, it may be necessary that you write it in an expanded form. Now we will try to simplify this equation for steady and two-dimensional flow. Steady flow and two-dimensional flow. Two-dimensional flow in xy plane. So if you have two-dimensional flow in xy plane, that means you have w equal to 0. Right? You have only u and v. There is no w component. So that means this equation is not needed anymore, because it involves w. In terms of the other equations, because the flow takes place in the xy plane, you can say that there is no gradient along the z direction. That means all the z terms, these terms I am circling, all the z terms that go away. In addition, we have assumed steady flow. Okay, so these terms are 0. And for steady flow, these terms 0. So we are left with equations x momentum and y momentum equation coupled with the continuity equation. So let us write those equations now. And of course, because we are considering that mu is a constant, so we can take mu out of the derivatives. So let us write now the continuity equation. Remember, we are considering a two-dimensional flow and incompressible flow. So the continuity equation, as you recall, for two-dimensional incompressible flow is this: x momentum so x momentum, you can see that x momentum you have rho u del u del x plus v del u del y is equal to minus del p del x plus these two terms plus bx. So let us write that rho u del u del x plus v del u del y Similarly, y momentum, let us recall the y momentum equation that we had just written. So y momentum will be rho u del v del x plus v del v del y is equal to minus del p del y plus the viscous terms plus by. So let us write that. Now this kind of two-dimensional flow, there are many practical examples, and we will consider one example. Steady, fully developed incompressible flow between two infinite parallel plates. So basically the situation is like this: you have two plates which are parallel to each other, and these plates have some width. These plates have some width. These plates have some width. It means that how can we consider these plates to be of infinite width? The situation is that we have to consider the width, and if the width is much greater than the other two dimensions, then we can call it infinite width. So infinite means, as engineers, we do not face with infinity, but what we see is that if it is much larger as compared to the other dimensions, then we say that these are infinitely long plates. So if it is of infinite width, then you can neglect the phenomenon in the z direction, where your coordinate axes are such that you have x axis, y axis, and this is z axis. In addition, we make an assumption that we are dealing with laminar flow. If we are dealing with turbulent flow, the physics gets complicated because the length scales, time scales involved. First of all, it is you have to consider the time scales of the turbulent flow, you have to consider the length scales of turbulent flow, those are more complicated matters. So we are not going into that, and here we are assuming that it's a laminar flow. So because it's a laminar flow, we will, and because we have restricted the discussion in this particular coordinators workshop only within laminar flow, we will not be going into the issues of turbulent flow. In our main workshop, we will of course be touching on some of the important issues of turbulent flow. Now let us draw the plate schematically like this. Let us say this is the center line, and h is half of the height. Let us set the coordinate axis such that this is x axis and this is y axis. Z axis is of no importance to us because the width of the plate is much larger than h and L, the length of the plate. Now, what is the physical phenomenon that is happening as the fluid is entering the plate? Let us say the fluid is entering the plate from a far stream, and once the fluid encounters the plate, what happens? A boundary layer starts growing from the edge of the plate. So two plates and a confinement created between two plates. This situation has some similarity with one plate. The only difference is that, there are many differences. One important difference is that you have boundary layer growing from the two sides here, from the two plates, whereas for one plate the boundary layer grows on one side and there is infinite free stream on the other side. So the boundary layer grows from here and the boundary layer grows from here. Now this region where the boundary layer grows, the velocity profile changes continuously. How the velocity profile changes, how the pressure profile changes, and how the wall shear stress changes, these are three very important questions. Because of lack of time, I am not going to discuss about these three important points in the coordinators workshop, but I will make it a point to discuss about this very thoroughly in the main workshop. So it is important that how these three quantities, you please think about that in your leisure time, that how the velocity profile, the pressure profile and the wall shear stress profile, how these change as the fluid is, as you are traversing across this developing region. Developing region or entrance region is the region in which this boundary layers are growing. Now one important observation that we can make irrespective of or independent of details of the discussion is that when you have flow over a single horizontal flat plate, you have a constant u infinity. Here you don't have a u infinity like this. You have the velocity in the core region. In the core region, the fluid is moving. This is like u infinity. U infinity, so if I draw it like this, you have the boundary layer here, you have the boundary layer here. Outside the boundary layer here, whatever is the velocity with which the fluid is flowing, that is like u infinity. But this is not a constant, because as you are moving along the x direction, what is happening? As you are moving along the x direction, the boundary layer becomes thicker and thicker. So more and more fluid is slowed down. To compensate for that, in the core region, this is the core region, in the core region fluid must be accelerated to make up for the loss of mass flow rate over the boundary layer. That means that the fluid in the core region is continuously changing its velocity. So if you give it a name u infinity, fine, there is no problem, you can still give a name, but that u infinity is a function of x, that is no more a constant u infinity. So fluid in the core region is continuously accelerating. There are issues associated with that. In the core region you can apply the Bernoulli's equation for example, but within the boundary layer you cannot. Now you come to a region you come to a region where the boundary layers have merged. Once the boundary layers have merged, see, till the boundary layers are growing, what is happening? Till the boundary layers are growing, what is happening? That the fluid within the boundary layer, this fluid feels the effect of the wall, right? Boundary layer is the layer within which the viscous effects are felt, and viscous effects here mean the effect of the wall, which is propagated by virtue of viscosity within the fluid. So the shaded region, it feels the effect of the wall, but the fluid in the core region, this does not feel the effect of the wall. However, when the boundary layers have merged, then the entire fluid feels the effect of the wall. The entire fluid then feels the effect of the wall. When the entire fluid feels the effect of the wall, it is called as a fully developed flow. So this is called as fully developed flow. So when you have a fully developed flow, you have a velocity profile, and this velocity profile will not vary with x. So if you draw the velocity profile at another x, let us say at this x, you will still get the same velocity profile. Till the flow was fully developed, the velocity profile would have been continuously changing. But once the flow is fully developed, the velocity profile will not change continuously. That means when the flow has become fully developed, u becomes a function of x only. U is not a function of x, u becomes a function of y only. So we have understood what is a fully developed flow qualitatively. The developing flow we have not discussed in this coordinators workshop, but we will be discussing it in the main workshop with some physical insight. Now our objective is to not discuss in details about fully developed flow and developing flow, but obtain the velocity profile in the fully developed flow region using the Navier-Stokes equation. So let us get into the Navier-Stokes equation. So let us get into these three equations which are of importance to us. First of all, for fully developed flow you have del u del x equal to 0 for fully developed flow. Because u is not a function of x. If u is not a function of x, del u del x equal to 0. That means del v del y is equal to 0. This means v is not a function of y. V is not a function of y. Can you tell from here? Let us draw the x and y axis and all this. This is x, this is y. This plate is y equal to plus h, this plate is y equal to minus h. Can you tell from here what is the value of v? V is not a function of y. That means if you can find out the value of v at some value of y, that value of v will remain same at all values of y, because v does not change with y. So at y equal to h, what is v? What is v here? V is 0 here. Why v is 0 here? Because of it has nothing to do with viscous effect. No penetration boundary condition, right? Many times this is very confusing. This has already been discussed by Professor Ghosh-Maulik, but I am again repeating that at the solid boundary you have velocity u equal to 0 because of the no slip boundary condition, but even if there was slip at the wall, v would still be equal to 0 because of the no penetration boundary condition. That is, fluid cannot penetrate through the solid boundary. It could penetrate through the solid boundary if there are holes. If there are holes or pores, then it could penetrate through that boundary. So then v will not be 0. But here there is no hole in the plate. So fluid will not be able to penetrate through the wall. That means V is 0. So we can write V is 0 at y equal to plus h or minus h at the top wall and at the bottom wall. That means what is V? That means V is equal to 0 for all y. The reason is that V is not a function of y, we have already proved. So if V is 0 at some value of y, that V should remain at all values of y, because V is not a function of y. Okay, so V is 0, that we have additionally proved for fully developed flow. So let us see how we can simplify these equations by considering del u del x equal to 0 and V equal to 0. So x momentum equation, del u del x equal to 0, fully developed flow. Then V equal to 0, we have just proved. Consider the right hand side. If del u del x is 0, its second order derivative is also 0. So del square u del x square equal to 0. And let us assume that there is no body force along x and y, so that these terms are 0. Now let us come to the y momentum equation. In the y momentum equation, you have, because V is 0, these terms are all 0. So if there is no body force along y direction, you can argue that gravity may take, gravity may be there acting along either positive y or negative y direction. So if you are there having the body force along y as, say, gravity force as the body force, then this will give just a hydrostatic pressure variation along y, this equation. So you can define a pressure, an equivalent pressure P star, which is like P plus rho g h, and gradient of that is 0. So this h takes into account, or y takes into account, the height. So this P star is called as piezometric pressure. Okay, so it is depending on whether you are accommodating for the body force, whether it is important or not, you will have either del p del y equal to 0 or del minus del del y of p plus rho g y equal to 0. So whether you are taking the body force into account or not, the only difference will be either there will be p, or in place of p there will be p star, which is p plus rho g h or rho g y, whatever. Okay, so in the x momentum equation, you can deal with either the pressure gradient or the piezometric pressure gradient, depending on whether you are accommodating the effect of gravity into account in the body force or not. To make matters less complicated, let us assume that body forces are not important. If body forces are not important, we will deal with P and not with P star. Okay. Now if body forces are not important, then from this equation what you will get? You will get del P del y equal to 0. If del P del y is 0, that means, what does it mean? It means that P is not a function of y. P could be functions of what? P could be functions of x and y. But we have just now proved that P is not a function of y. Because P is not a function of y, P is a function of x only, and therefore we can write del P del x in the x momentum equation as dP dx. Now I have already told that to simplify the matter, we will consider there is no body force, just to get the concept. To get the concept, bringing piezometric pressure is not necessary. Okay, we can always complicate it. So I can make it more complicated by saying that the channel is inclined, or the channel is vertical, or something like that. Let us not bring all those into account, because then we will just replace P with P star, but there is no new physics that is discovered. So always remember this thing, to illustrate a principle we should keep the situation as simple as possible, so that the principle can be illustrated in a better way. Always a simple thing can be twisted. As teachers, it is very easy for us to make things complicated. It is very difficult for us to make things simple. So always try to make things simple as much as possible and do not unnecessarily complicate. If you want to convey a message, please convey that, try to give an example that conveys just that message, but not too many peripheral things. So we will not get into too many of the peripheral things, we will just assume that body forces are 0. If body forces are 0, then del P del Y is 0. That if there is no body force along y direction, you have del P del Y equal to 0. That follows directly from this equation. Okay. So P is not a function of y only. If P is not a function of y, P is a function of x only. So in place of del P del x, we can write dP dx. So our only equation that remains is the x momentum equation. What is the x momentum equation now? So let us write the x momentum equation. This equation. So left hand side becomes 0, right hand side becomes minus dP dx. No, del P del x becomes dP dx, minus sign is still there. I mean, P is a function of y, that does not mean that it has a power of changing plus to minus sign. That kind of power is not there with P is a function of x only. Okay. So it's still the minus sign is minus sign, it does not get changed. Okay. So this is minus dP dx plus mu. U is a function of y only, because U is not a function of x for fully developed flow. So mu d2u dy2. Okay. So what we have achieved by this simplification? We have achieved one important thing by the simplification. We had converted the non-linear form of the Navier-Stokes equation to a special form which is a linear form, because the left hand side which gave rise to non-linearity that has become 0 because of the simplification. So fully developed flow will mean that the left hand side is identically 0, and that makes the Navier-Stokes equation perfectly linear. So then let us try to solve this equation. So d2u dy2 is equal to 1 by mu dP dx. This is a function of what? X or y? This is a function of y only. This is a function of what? This is a function of x only. Because P is a function of x only, so dP dx is also a function of x only. So you have a function of y only is equal to a function of x only for a general case when it is possible. Possible only when each is a constant. Otherwise, some x in one side cannot balance some y in the other side, some y in one side cannot balance some x in the other side. So this means each equal to constant. Let us say that the constant equal to c. So d2u dy2 is equal to 1 by mu dP dx is equal to c. Let us draw the schematic of the problem in association with this. This is the top plate, this is the bottom plate. this is our y axis, this is h. Because of the symmetry of the problem, we can solve only one half of the problem. The velocity profile in the other half will be just symmetrical to each other, to that. So now what we can do, we can integrate this. So du dy is equal to cy plus c1 and d2u and u equal to cy square by 2 plus c1y plus c2. Now we can find out c1 and c2 from the boundary conditions. Boundary condition at y equal to 0, what is the boundary condition? Y equal to 0 is here. Our domain is the shaded region. At y equal to 0, you have du dy equal to 0 because u is maximum there. The maximum velocity is at the center line, so you have du dy equal to 0. So at y equal to 0, if you put du dy equal to 0, then from this equation what you get is c1 equal to 0. And the second boundary condition, at y equal to h, what is u? U is 0, that is the no slip boundary condition. So that means 0 is equal to c h square by 2 plus c2. So c2 is minus c h square by 2. So u becomes c by 2 into y square minus h square by substituting in this equation c1 and c2. So we can see the first observation is that the fully developed velocity profile is parabolic. It is quadratically varying with y. So it should look something like this. Parabolic velocity profile. Okay. Now this is the velocity profile expressed in terms of dp dx, because what is c? C is equal to 1 by mu dp dx. So let us now come into the pressure profile. C is a constant, mu is also a constant, that means dp dx is a constant. That means P is a linear function of x in the fully developed region. So P varies linearly with x in the fully developed region. So we have now understood the velocity profile and the pressure profile in the fully developed region. The velocity profile, u is not a function of x, u varies quadratically with y, and p is a linear function of x such that dp dx is a constant. So we have expressed u as a function of dp dx. It may also be interesting to express u as a function of u average. So how do you define the average velocity? U average? U average is integral u dy by integral of dy. So integral of u dy from minus h to h, integral of dy from minus h to h. So this is because there is the upper half and the lower half is symmetric, it is as good as 2 integral u dy from 0 to h and to h. So these 2 gets cancelled out, integral u dy c by 2 integral of y square minus h square One important observation about the velocity profile, and it is an elusive observation, that it appears that y square minus h square, because y is less than h, maximum y is h, this term is negative. But actually c has to be positive, c has to be negative, so this is negative to make u positive. So for flow taking place in the positive x direction, you must have dp dx as negative. This is called as favorable pressure gradient. Okay. So that is the observation regarding the sign of c. C itself is negative. Now you can write this as c by 2 this is, let us quickly complete this. This is h cube by 3 minus h cube. So c by 2 into minus 2h cube by 3. So that gets 2 gets cancelled out. So what is c? C is equal to minus 3u by 3u bar by h cube. Minus c is equal to minus 3u bar. Oh, there is a division by h, that is there. So right. So this divided by h is there, right? Divided by h, so this becomes h square. H square. So in place of u is equal to c by 2 into y square minus h square, in place of c we can write minus 3u bar by h square. So u by u bar is equal to 3 by 2 into 1 minus y square by h square. This is the velocity profile in terms of the average velocity. Finally, we will conclude by calculating the wall shear stress. So what is wall shear stress? So tau wall, that is equal to mu into del u del y plus del v del x at the wall. Of course this term is not there, so mu del u del y at the wall, but we have to understand that we have to adjust it with a sign. When we write tau equal to mu del u del y, that y is the outward normal to the solid boundary, but here this y is inward normal to the solid boundary. So we have to adjust it with a minus sign here. So minus mu del u del y at y equal to h. So plus or minus depending on which wall. The top wall has normal minus y and the bottom wall has normal as plus y. So this is y equal to h we must write, not just any arbitrary wall. Depending on which wall, the normal direction is either plus y or minus y. So we can complete this. So u by u average is this. So this becomes minus mu 3 by 2 into minus 2h by h square. So tau wall, these 2 gets cancelled out, 3 mu. There is a u bar, so let us write that u bar, 3 mu u bar by h. Okay. So this is the wall shear stress. You can calculate the wall shear stress in a non-dimensional form, which is the friction coefficient. This is tau wall by half rho u square, the non-dimensional tau wall. So you can calculate this by simple algebra, and I leave it on you as an exercise. So write this as a function of Reynolds number. The CF as a function of Reynolds number. So this elaborated discussion was there to make you feel comfortable of using the Navier-Stokes equation for simple cases for coming up with an exact solution. A very similar consideration, just with a different geometry, a cylindrical geometry, is more popular in engineering because that considers flow through pipes. fully developed flow, fully developed laminar flow through circular pipes, which is known as Hagen-Poiseuille flow. This flow that we have discussed is plain Poiseuille flow, and the fully developed pipe flow is the Hagen-Poiseuille flow. So the for Hagen-Poiseuille flow, we have given you a tutorial homework. So it is just a very similar step, collection of similar steps, just the governing equations change, not in principle but in form, because there you use the cylindrical coordinate Navier-Stokes equation. Here we have used the Cartesian coordinate Navier-Stokes equation, and there because of the geometry we use the cylindrical coordinate Navier-Stokes equation. So I think we will take another 5 minutes. The description of the governing equations and how the governing equations can be simplified in their final form, that will be now discussed by Dr. Sukumar Poti.